Hello friends, I welcome you in lecture number 16 on partial ordering. In this lecture we will discuss one more problem on lattice. The problem is determine whether power set of a set S under inclusion relation is a lattice or not. So we are familiar with the power set of S. It is the set of all possible subsets of a given set S, and we have to check whether this power set is a lattice or not under inclusion relation. So we recall the definition of inclusion relation. If we have a inclusion relation on some set, then it is the set of all those ordered pairs AB such that A and B are elements of power set and A is a subset of B. So two elements of power set are related to each other if one element is a subset of another element, or two sets are related to each other if one set is a subset of another set. So if A is subset of B, then we can say that A is related to B, and if B is subset of A, then B is related to A. Here we have to decide whether power set of S is a lattice or not. So for that we have to take two elements in the power set of S, and we have to check whether least upper bound and greatest lower bound exist for any two elements which we have taken. So here we are not given that this set S is a set having which elements. We are given a arbitrary set, and we have to decide whether power set of an arbitrary set is a lattice or not. So we consider arbitrary elements in the power set. Let A and B be any two elements in the power set of S. This means A and B are subsets of given set S, and we have to check whether least upper bound and greatest lower bound exist for these two arbitrary sets which are subsets of given set S. Now it is clear that whenever we have two sets in the power set, then we will always have another set which contains these two sets. Suppose C is a set which is containing set A and B, or suppose A and B are subsets of some set C which is in the power set of S. Then this C is an upper bound. If C contains A and B both, then C is an upper bound of this subset having two elements A and B. Now we have to check whether this subset has least upper bound or not. Suppose there are more than one upper bounds for this subset, then we have to check whether this set of all those upper bounds has a least upper bound or not. So we claim that if C is an upper bound of the set containing A and B, then we have A union B is subset of C, and this is true because A and B are both subsets of C. Because A is a subset of C and B is a subset of C, therefore A union B must be a subset of C. We have this type of situation. Suppose this is set A, here I have set A and here I have set B. Then if I take their union, then A union B is also a subset of C, and it is also clear that A and B are subsets of A union B. So A union B is an upper bound of this subset having two elements A and B, and if C is any upper bound of this set, then A union B is a subset of C. This means A union B is the least upper bound of this subset having two elements A and B. Therefore least upper bound always exists in the power set of S under inclusion relation. So here we have shown that least upper bound exists, and we have to write systematically that let AB belongs to power set of S. Now we can write that clearly. A is a subset of A union B, and B is also a subset of A union B. That is, A and B are related to A union B. Therefore, A union B is an upper bound. A union B is an upper bound for this subset having two sets A and B. Now, suppose C is any other upper bound. Suppose capital C is any upper bound for the same set having two elements A and B, then by the definition of upper bound we must have A related to C and B related to C. That is, A must be a subset of C and B must be a subset of C. And if A and B are both subsets of C, then their union is also a subset of C. This means if C is any upper bound for AB, then it contains A union B, or A union B is related to C and A union B is also an upper bound for AB. This shows that A union B is the least upper bound. Therefore, least upper bound of the subset having two elements A and B is A union B. In other notations, we can write that A join B. These are the different notations. We can write in this way also. These are different notations for the least upper bound in a lattice. So least upper bound exists for any two sets which are subsets of given set S or which are elements in the power set, and least upper bound turns out to be union of those two sets. Now we check for greatest lower bound. So for greatest lower bound also, first we observe that if we take intersection of two sets, then their intersection is a subset of set A as well as set B. So from this I can say that A intersection B is related to A as well as B. This means A intersection B is a lower bound. A intersection B is a lower bound for this set having two elements A and B. Now we want to show that A intersection B is the greatest lower bound. So for that I assume that suppose say D is any other lower bound, or D is any lower bound for this set having two elements A and B. Now if D is lower bound, then D must be related to both the sets. Therefore D is a subset of A and D is a subset of B. Now if D is a subset of A as well as D is a subset of B, then we must have D subset of their intersection. So D is any lower bound and A intersection B is also a lower bound, and any lower bound is related to this particular lower bound A intersection B. This means A intersection B is the greatest lower bound for this set having two elements, or I can write in this way also. Therefore greatest lower bound of the subset having two elements A and B is equal to A intersection B, and this always exists in the partial order set, which is power set of a set S in this case. So what we have shown? We have shown that if we take any two elements in the power set of S, then the least upper bound as well as greatest lower bound exist for those two arbitrary subsets of S, and this least upper bound of two subsets of S turns out to be union of A and B, and greatest lower bound turns out to be intersection of A and B. We can use different notations also. This I can denote by A star B, or we can denote it by A join B also. So remember these different notations also, and this shows that for any two arbitrary elements in the power set of S, their least upper bound and greatest lower bound exist in the power set of S, and therefore power set of S is a lattice under the relation of inclusion, or under inclusion relation power set of S is a lattice where S is a set. So this is all about this session. I hope you like it. We will continue with lattices in upcoming lecture. Thanks for watching.